In this video, we will design, make and verify the impedance of a microstrip transmission line. Let's look at what we will be using to make our line. Here we have a 10 by 20 centimeters single-sided board. Single-sided means that it only has copper on one side, and this will be our ground plane. The thickness of the board, that is the height of the substrate, is 1.6 millimeters. The dielectric material is Fr4, which has a dielectric constant of approximately 4.5. We will make the actual signal line by sticking a strip of copper tape on the bare side. What we have added to the board are some via holes, which are connections between the top layer of the board and the ground plane. To make these, we first drilled some holes in the board. Then we put some copper rivets through them. A simple but effective way to make vias at lower frequencies. Now let's open AWR and TX line. To design our 50 ohm line, we need two main bits of information: the dielectric constant, approximately 4.5 for our Fr4 board, and the height of the substrate, which is 1.6 millimeters. Let's also select copper as our conductor and an operational frequency of 400 MHz. Unlike the coaxial case, here we are not verifying the characteristic impedance of a ready-made line. We want to set a target impedance of 50 ohms, and TX line will tell us, based on other parameters that we have entered, what the width of the line should be for such an impedance to be achieved. So let's click on the right pointing arrow and get our width, which turns out to be approximately 3 millimeters. We can add a few extra bits of information such as the loss tangent of the dielectric and the thickness of the copper used for the signal line. But as you can see, at relatively low frequencies, these additional parameters don't make a significant difference. Our next step is to create a virtual microstrip line and test its characteristic impedance with a virtual VNA. But before we do this, let's get the effective dielectric constant from TX line. From this value, we can work out the velocity factor. With a bit of algebra, we find that the frequency at which the electrical length of our line is lambda by 8, or 45 degrees, is 203.7 MHz. TX line can even help us check that we got this right. We simply keep everything as before, but we set the frequency to 203.7 MHz and the length to 10 centimeters. We then click on the left pointing arrow and, hey presto, TX line confirms that the line is indeed 45 degrees long. Let's now create a new schematic, add our virtual VNA, and then add a microstrip line. We also need to add a substrate element to provide all the necessary specs for the MLIN element to work. Let's set all the parameters of the substrate as we did in TX line, and set the width of the microstrip to 3 mm and the length to 10 cm, since we will be placing it across the entire length of the board. As usual, we set up an S11 measurement on a Smith chart. We set the test frequency to the one at which our microstrip line is lambda by 8 long, which is 203.7 MHz. We then add a marker, denormalize the impedance readout. And here we have it, an imaginary part which is indeed very close to 50 ohms. Note that, in this case, the real part is not 0 since the simulator is accounting for losses, mainly through the loss tangent of the dielectric. Well, I think that we are now ready to make it real. Let's go. First, let's cut a strip of copper tape, approximately 11 to 12 centimeters long. Then, let's cut a 3 mm wide piece out of this strip. You can do this by measuring 3 mm with a ruler at two different points and marking those points on the strip. Or you can use a caliper. Open it to 3 mm and then use it to mark 2 or 3 points, 3 mm away from the edge of the line. Next, use a knife to cut the strip. Make sure that you take precautions to prevent injuries. The tape has adhesive on the underside, so we can simply stick it on the board, making sure that it is approximately 2 mm away from one of the vias. We then cut off the extra bits. And here we have a homemade microstrip line. Now, to test it, we can use a board edge connector like this one. This fits our board quite snugly, so, for our first test, we won't even need to solder it. This makes life easier since, should our line not turn out to have the right characteristic impedance, we can easily replace it. Now if we connect our VNA and measure the S11, then add a marker and set its frequency to 203.7 MHz. The modulus of the imaginary part of the impedance, which represents the characteristic impedance of the line, is approximately 49.8 ohms. This is very close to the value that we got from the simulator. The real part is also close to the simulation prediction. Now that we have verified that our line is operating as expected, let's solder the connector and get ready for our next experiment.